Hello and welcome to this low-level JavaScript series where we're attempting to build the world's first RISC-V CPU on an FPGA using the TypeScript programming language. Now, we're actually on episode 8. We're up to episode 8 now, so we're quite far down the line. And at this point, we're still building an emulator rather than actually building on the hardware right now. And this emulator, just to catch you up if you haven't seen before or you haven't watched for a while, the emulator is actually a very low level emulator. So we're modeling like clock cycle by clock cycle, we're modeling the pipeline in the CPU, and we're modeling all the different modules that we'll have in the hardware, plus all the signals inside those modules, what they take in and what they put out. So we're trying to get kind of as close to what we're going to write for the FPGA as possible, while still being able to explore the architecture in a sort of really easy, clear way, and also to be able to debug kind of the design in a nice environment with a lot of debugging tools and the ability to just throw breakpoints down and see what's going on. So just to get rid of some of the complexities that we'll have on the FPGA. So we've got the best fighting chance of succeeding and not getting stuck in FPGA hell, as it were. Okay, so today we're going to be talking about CSRs, and they are the control and status registers. And yeah, they kind of are exactly what they sound like. They are registers inside the CPU that control and give you status information about the CPU. And it's kind of a big topic. It's kind of not a big topic in some ways because, yeah, they're kind of just a set of registers that you can read and write to. You can interact with them with a set of 6 or so instructions, which allow you to do various combinations of reading and writing and setting and clearing bits and doing all this kind of things. So we're going to kind of get into that. And of course, you know, in the last episode, we kind of got to the point of like Turing complete with the processor. We implemented conditional branches, we have unconditional branches, we have all the load stores, we have all the arithmetics, and we have most of the load. I already mentioned load, but we have also like the immediate load kind of instructions, like the upper immediate load. We're missing still add upper immediate program counter, which is kind of just I haven't found a good video to put it in because it's just like this one instruction. It's not going to take that long to do, and it's kind of something we've basically done before. It's a combination of load upper immediate and add essentially. So what I might do is just implement that off camera before the next episode, but we'll see. Maybe I'll just do it in the next episode, but we're probably going to have quite a bit to cover there. So let's talk about follow-up business. So a couple of points. I fixed a bug that I introduced in the last episode where I implemented the greater than or equal to as greater than. That's obviously a problem, and I kind of stumbled over my words a bit. I made a claim that greater than or equal to is the opposite of less than, right? It's just like you can just flip the condition and then you'll get the greater than or equal to, and that actually is true. But I kind of somehow confused myself in the moment. I blamed that I was a bit tired in that moment, but I kind of walked it back and ended up implementing the wrong thing. So what I've done is I've just implemented it in the correct way, in the simple way, in the way that means that we don't have to build that much extra hardware. We really can get away with just pretty much getting everything with the less than, and then just, you know, moving operands around and flipping that condition. Okay, so I also renamed the sort of main top level class in this, which would be the top level module in the FPGA. Which kind of links all of the different pipeline stages together and does the orchestration. It may be that will become more of a control unit in the FPGA. I'm not sure, like we might have one more level between that and sort of like the top overall system. We'll see about that. At the moment, keeping it as simple as possible. I finally named that the right thing. So it was called RVI32 before, and that's a mistake that I made all the way back in the beginning and sort of corrected but didn't actually correct in the code. So I've done that now. Very minor change, but it's there. Renamed the instruction fetch file to just be fetch, just because, yeah, it's kind of implied, right? We're fetching instructions. And the most important thing is that I added the concept of a register bank. And I'm going to give you a quick look at what that actually is and why I did that, because it's kind of, I actually think it's one of the most useful little abstractions that I've added in. It's only useful in the emulator, right? It has nothing to do with the actual hardware. But yeah, so a register bank is just a class that holds a set of named registers. So it has this registers object. It's a record of string keys to register 32s. It's got an add register method that takes a name and an initial value, which can just be 0 and is just 0 in most cases. That will create a register, assign it inside the registers object, and return the register. Pretty simple. There's also a latch next, right, which just latches all the values in all those registers. And there is this method called getValuesOut, or getValues object. And it's got some generic stuff going on. So it takes a generic here, ks, which extends string. And basically what it does is it iterates through this object as a set of entries. So when you do object entries, if you don't know, when you put an object in object entries, it converts it to an array of arrays where the first element is the key and the second element is the value. So it's a pair, basically. It's an array of pairs. And so you can iterate it just like an array, and then you can do a reduce operation to transform that back into any other structure. And basically what I'm doing here is really simple. I'm just iterating through all the registers and making a new object where they have the same name, but they just have the numerical value, the currently latched value inside the register. So yeah, so what you'll notice is this is basically the construction we have in every pipeline stage. So in every pipeline stage, we have a bunch of registers. We assign values in compute, the compute method, and then we have a latch next method in every pipeline stage in which we latch all of the values of the registers. And then at the end, we have this get values out, or get decoded values out, or something like that. And it provides an object with all of the registers, but then with their actual named value. And so this kind of mirrors that. And basically the idea is to just encode all of that kind of stuff. So what I'll do is I'll just show you here the decode stage. So we've got all the same registers here. They're still just living on the class, but I've used this this regs, which is an instance of register bank, and I'm just calling add register instead of instantiating a new register 32, and then I give the name, and so that part's the same. You assign and everything the same in compute, but now latch next is just a dispatch to regs latch next, and when we do get decoded values out, we actually only need to provide this generic with all the keys that we expect to be in that object. This is kind of a bit of a weird bit of TypeScript, because it's like it's kind of going around the type system. It's sort of like forcing the type system to say that the object has these keys in it, and it does have these keys, but it just means that we could also put something that isn't there, like this isn't. Can't use a quote there. This isn't a key. And the problem is that if we did this and we went into execute and we looked at the decoded, it would tell us that there is a this isn't a key here, and it would be a number, but it's not true. That doesn't exist. But we kind of we're going around the type system using these generics. And that's a trade-off I'm making, because I believe that by doing it this way, I'm actually saving myself a lot of bugs that I've been creating throughout the episodes. So I was kind of, every time we were adding a new register, I would come in here, I would copy-paste the register, I would change the name, I would assign it here, and then here in latch next, I would copy it and latch the value, And then here we would have an object where we'd make the name of a key, and then we would get the value over here. And very often what I would do is I would change one name but not the other one, or I would forget to put the name in here, or I wouldn't latch it, and we were just getting these problems. And now this kind of removes a couple of those manual steps. And yeah, so I think that that's going to save me a bit of headache, and I'm okay to make the trade-off there that I know that it's not perfect in the type system, because yeah, I think I won't mess this part up. I probably will now that I've said it, but that's the idea. So that's why I wrote this register bank thing. I've put it in all the pipeline stages. I think it's going to be a quality of life thing. So with that out the way, let's move on to CSRs. Now, as I already mentioned, CSRs are control and status registers, and let's just dive over to the spec and take a look at what it has for us here. So if we go to this control and status registers page, they're part of the system instructions. So that's the opcode that encompasses these. Yeah, one thing I'm not making clear here is that we have control and status registers, and we have instructions that allow us to manipulate those control and status registers. And what this page in the document, or this little chapter in the document, is really describing to us is the instructions that manipulate the CSRs. And to actually get a good description of the CSRs themselves, we're going to have to go to the other document, the volume 2 of the specification. And we haven't looked at that yet, but we're going to have a little brief look at that today. So what it tells us is system instructions are used to access system functionality. They might be privileged access to the machine and are encoded using the I-type instruction format. These can be divided up into two main classes: those that atomically read, modify, write control and status registers, and all other potentially privileged instructions. And I'll show you the distinction between those two things in a little bit. So CSR instructions are described in this section, with the two other user-level system instructions in the following section. And those are the environment call and breakpoint instructions, which we might have talked about briefly. Okay, so CSR instructions. So what it tells us here is they're going to define the full set of CSR instructions, although in the base user level ISA, only a handful of read-only counter CSRs are actually available. So this is going to, in the next couple of episodes, we're going to start talking about kind of the different levels of the ISA and the different privilege levels. And I've mentioned earlier that we're not like implementing like privilege levels in the CPU, and that's still true. We're not going to like the level of adding multiple privilege rings there, so that you could run an operating system or something where you would have a kernel running on one level of privilege and the user stuff on another. And no, we're not really going to go for that, but we do kind of actually need to implement like two levels. We have the user level, and we'll have something called the machine level. And for all intents and purposes, the machine level stuff, we're not going to have anything that's like really specific in there for machine level, and we're only going to have a handful of registers in the machine mode as well. So kind of the distinction isn't really going to be there for us. Like this is a bare metal CPU, so you're going to kind of be able to do everything, and you don't really need to go between these different levels. But again, we'll get into that shortly. First, let's just take a look at the instruction format itself. So here you can see it's using the I-type in the place of the immediate, the 12-bit immediate that we normally have. We have the CSR, and that's actually like its address. It's the CSR address. So these registers, they're not like the general purpose registers that we have, the 32 general purpose registers that we have for integer instructions, right? They're not like those. They're also not like the program counter, although I guess it's more like the program counter because it's in sort of inaccessible register. But basically, these registers, they live in their own sort of address space. So there's this 12-bit address space that is specifically targeted to CSRs, and it's not part of main memory, and it's not the same address space as like the 32-bit space of main memory. It's its own thing. And actually, you know, some of the stuff that we're going to end up doing with like memory mapped IO, you could potentially do it via the CSR interface. And maybe we'll explore that, I'm not sure. But, you know, memory mapped IO is also fun, so there's a possibility there. And some stuff we'll probably need to do via memory mapped IO anyway, simply because RISC-V doesn't give you the facilities to do it otherwise, especially when it comes to like setting 64-bit numbers and things like that, which we'll have to do sometimes. Anyway, without getting off topic, we also supply RS1 sometimes, and we've got funct3 that's going to allow us to distinguish between the different kinds of instructions that we have for the system opcode, and we deal with the destination register. So we have these 6 different instructions, and really it's only 3. You can think of it as being 3 different functionalities, and we have a register variant and an immediate variant of each of them. So we have CSR read write, and then we have CSR read and set, and we have CSR read and clear. And the idea here with each of these, well, let's just go one by one. And one thing I'll say just straight off the bat is that this couple of paragraphs that follow here are kind of tricky to get your head around. They seem simple when you first read them, but they take a little bit of thinking to get to the point where you get what's meant by all the mechanics of it. So CSR RW, which is atomic read and write CSR, that instruction atomically swaps values in the CSRs and integer registers. So we can put something in X5, and we could use this instruction to swap the value that's in X5 with something that's in one of the CSRs, switch them around. Can be useful sometimes. It reads the old value of the CSR, and then it 0 extends the value to X length bits. Now this part here, this X length bits, X length here refers to the native width of the CPU. We're building a 32-bit CPU, so all X length is actually 32 bits. Now, were we building a 64-bit CPU and we were implementing these 32-bit instructions, of course, what would happen is we would pull the value out and we would have this 32-bit value and we need to put in a 64-bit register. So we need to choose to either sign extend or 0 extend it. And basically, when we're dealing with the CSRs, we do 0 extension, which basically means you just put zeros at the top. Nothing super special, but it means that you don't preserve the sign bit and do all of that kind of stuff. Because in this case, you don't really need to do all of that. Like, the reason it's done in the integer instructions, all the other kinds of instructions that require extension, is because the sign extension is generally like just a bit more useful when it comes to doing all of the integer and logical and arithmetic operations. So that's kind of the use there. That's why they're 0 extended, because it's just more useful to be 0 extended in this case, right? You don't want to have to get rid of the sign extension bits. Anyway, so it extends it, which it won't happen in our implementation, and then it writes it to RD. The initial value in RS1, so that's our source register, that's the one we want to swap the value with, that is then written to the CSR, and this all happens atomically, right? So essentially in the same clock cycle. I think for our CPU it will all happen in the same clock cycle, because we won't use a memory or something like that for these. These will really just be little registers, so we can just do that operation in one clock cycle. Now, there's a little catch, and that is that if RD is X0, i.e. it's the 0 register, then the instruction doesn't read the CSR at all, and it doesn't cause any side effects that might happen by reading the CSR. Now, that's one of the tricky things here, is that like RISC-V allows these CSR registers to potentially have side effects. So like when you read and write CSRs, something might happen. An external event might happen. So for instance, you can imagine that we could make a CSR for LEDs on the board, right? And that by reading, or simply by reading something, maybe we turn the LEDs off. Maybe like that's how you can control turning an LED off. It's kind of a weird mechanism, but it's just an example. That's legal, right? But if you said that when you do this atomic swap, that your destination register is X0, i.e. the 0 register, the constant 0 register, then it just wouldn't do it. It wouldn't have the effect. It wouldn't even do the read. What it would do is put the value from RS1 inside the CSR, if the CSR is writable. So that's kind of interesting. That's something to keep in mind. Now, then we have CSR-RS, which is atomic read and set bits in CSR. Now, what this one does is it reads the value of the CSR, puts it into RD. The initial value in the integer register RS1 is treated as a bit mask that specifies the bit positions to set in the CSR. Any bit which is high in RS1 will cause the corresponding bit to be set in the CSR, if that CSR is writable. Other bits in the CSR are unaffected, though CSRs might have side effects when written. So that's pretty simple, right? We're not swapping any values, we're reading the value out, and we're potentially writing some bits high into the register. So yeah, that's quite useful if you're writing to a control register where specific bits have specific meanings. And now the CSR-RC is kind of the inverse of that. It's not really the inverse, but it's the complement, in such that it clears bits instead. So any bit that you have set in RS1 specifies the bit that you want to clear, set to 0, in the register. And same kind of story with everything else. Now this also has a caveat, and that is that for both of those, for read and set and read and clear, if the source register is X0, i.e. it's the 0 register, then the instruction doesn't perform any writes, and it doesn't cause any side effects that would happen from a write, such as raising an illegal instruction exception on accesses to read-only CSRs. So so that's quite interesting as well. These are two quite tricky things that we need to keep our eyes open for. And of course it says like this is not saying about the value 0, right? So if RS1 specifies a register that has the value 0, that's going to write it, right? It's going to write 0 into the register. So it's not about the value, it's about specifically the X0 address register. Okay, then we have the CSR RWI, CSR RSI, and CSR RCI variants, which are the immediate versions of these. And the difference here, I won't go into the paragraphs at the moment, the difference here is that these 5 bits that we have to specify RS1, we instead treat those as an immediate value. And we 0 extend this immediate value up to 32 bits. So you have 5 bits there. You can only specify numbers from 0 to 31 doing this. So you don't have a large range of values to set here. But this can be useful in some circumstances. And so you have that. And it has the same for all of these things, right? It has the same kind of caveats. So for let's see here, for the read set immediate and the read clear immediate, this field is, if it's 0, then the instruction doesn't write to the CSR. So it's actually the same logic is applied here, because that U immediate, that's actually just that is the address of RS1, right? It's before it's been extended, but that is just the address of RS1. So we can pre-compute if any of these instructions, no matter if they're the register or the immediate, we know if they're gonna do a read or do a write. So we know that we can use that, check the 0 value of that, which is nice. It's really well thought through design. This is exactly where you can see that the design has been really well thought through. Okay, so that's kind of the CSRs in a nutshell. It's quite a lot of information. We're going to go into this a bit more, and we are going to go and implement this very shortly. So if it's not clear, it will become clear. And if it's not clear, also don't worry, because I had to read this a lot, and I had to kind of make a lot of notes, scribble down a bunch of conditions to really see if I got it. And yeah, I hope that I do now have it. There's some stuff about how there are pseudo instructions for doing just like simple versions of these, like CSR read, where basically you can provide a destination register and a CSR, and that just gets encoded with this like the right value being when doing a read set and having the set be the X0 register, right? So then you know you're not going to do a write, so it's like it's only a read, it's a pure read. Okay, there are actually only 3 required, or 6 if you count it like that. There are only 6 required CSRs in the user level. Those are something called RD cycle, RD time, and RD instret, which is instructions retired. So cycles is easy. Cycles is literally a counter that contains the number of clock cycles that have elapsed since a certain period of time. It doesn't have to begin at 0. It kind of makes sense for it to begin at 0, but it doesn't have to. It just has to begin at some point and count up linearly. Now, time is pretty much the same kind of thing. I mean, it doesn't express that you have to count clock cycles. Cycle also doesn't express that you have to count clock cycles. You just have to count at some interval, and it has to be, the number of clock cycles. So, okay, it does actually say it has to be clock cycles. But time doesn't have to be anything like really specific. It doesn't have to be a count of like clock cycles or anything like that, right? And the reason it doesn't have to be clock cycles is because, we're building an extremely simple CPU. That's the idea here. Simple as possible, super, like, you can imagine it basically being a microcontroller. And, RISC-V is not only designed for chips like that, it is designed to allow for microcontrollers. It's also designed to allow for like really powerful superscalar multi-threaded, like multi-core chips. And if you're building a chip like that, you can have variable clock frequency. And because of that, you cannot just put your clock cycles into a counter and say that there is a way to get directly from that number to like some number of seconds that have elapsed since the beginning of the CPU. And RISC-V says that it's pretty important to have some sort of counter functionality, some sort of time keeping functionality, so that that's just useful. That it really is useful to have the ability to know time has elapsed. So yeah, they mandate you need to build a timer, and for us, it's fine. We're not going to have a variable clock frequency, so whatever our known clock frequency is, we can basically expose that somehow, and then the user can basically read our clock cycle counter and do some math and figure out okay, this is what the time is based on that. And that is a valid implementation, and so for us, these two registers, they'll just be the same thing. We'll just keep track of the clock cycles, and we will expose like our clock frequency, and then software can figure out how long time has passed, how much time has passed. The thing to keep in mind here is that these counters are 64-bit. They're not 32-bit counters. And so there are two CSRs for each, right? They allow you to get at the most significant 32 bits and the least significant 32 bits. Yeah, it's quite nice. So you can basically, within 2 or 3 instructions, well, within 2 instructions, but if you create a little loop with 3 instructions, you can read the full 64-bit value and do a comparison and make sure it is actually what's the word I'm looking for? Stable. That it hasn't, like, the top 32 bits haven't changed in that time. I hope some of this makes sense. You have to think that, clock cycles, they go so fast that if you only had 32 bits, you could really easily overflow that number. And if you have 64 bits, it's like, it just becomes sort of ridiculous. You would have to run this so long to, and I'm not going to try and perform the calculation here, but because we don't know the clock frequency, but you would have to run it for so long to overflow a 64-bit counter that it just doesn't even matter. So yeah, and then we have this other CSR, which is the instructions retired. This one refers to the number of instructions which have been executed on the CPU. Really easy for us to keep track of. If you have a more complex processor that is able to do out of order execution, that is able to do like instruction fusion and like all of these like more complicated processor topics, then obviously this gets a little bit more complicated as well. But for us, this is easy, right? Whenever an instruction moves through the pipeline, we basically execute instructions as they come, like naively. We don't do any optimizations there. We won't, maybe we will one day, but I don't think so. Yeah, then we're just going to increment the counter. So super easy. And yeah, I think that is just about everything we really need to know. This is the little bit of assembly code, by the way, for reading the 64-bit timer. So that the top 32 bits are in X3 and the bottom are in X2. So basically you would read the high part first, then you would read the low part, and then you read the high part again into another register. And if they're not equal, then you just try the whole thing again, because it means that you got some unstable point, some unstable point. Yeah, and you just try again, because it's very, very unlikely that you would catch a transition 2 times in a row. So you can really quickly read the counter this way. So that's it. I recommend going in and reading all the information here if you're interested, because there's a lot of useful information. And for now, I think we should start diving into the code, but shortly we're going to actually take a look at the volume 2 specification, because that has a lot more detail about the address space and how to decode the addresses and things like that. So we're going to need it pretty soon. All right, I think I've covered a ton of this now. And I've still got some of my test code in here, so I'm just going to delete that, and we're going to do it from scratch. So I'm going to add the same folder I just deleted, but without any of the internal files there. And I'm going to do index.ts. And what we're going to do here is we're going to make a class for the CSRs, and I might change this in the future. Yeah, this might change, but for now we'll make a class, call it CSR interface, I think. Yeah, because then that matches closer to the like the system interface, which is the bus of the whole system, the memory mapped IO. And what we're going to have in here for now is going to be like a read method, right? Because we read the CSR address space. Have an address that's a number, and we'll return a number. So for now I'm just going to pen that in like that. And we'll also have write, and we're going to write. I just want to check the system interface now for. We do address first. Okay, so address. And value, which will be a number. And we don't return anything here. I won't keep that in, but just for the illustration purposes. So yeah, that's what we're going to have. And then we're going to need these. We're going to need two registers here, right? We're going to need the cycle counter, and we're going to need the instructions retired counter. But these are actually 64-bit counters. So our register 32 is not a good fit for this, right? We could potentially use it, just have two of them together, but then we're going to have to worry about addition and like doing carry between the low 32 bits and the upper 32. So I think what I'm going to do here actually is just create a class called register 64, and we'll make a 64-bit register. So let's do rename. Just copy this here. I don't think we're going to need to keep a lot of this. Pretty much everything is going to change here. We won't have a uint32 array. Instead, we will have a big int value. And this is how you specify a big int. A big int is an arbitrarily sized integer. We've actually spoken about them already on this channel, on this series, and then we got rid of them. But now they're back in. So this is going to be the next value. Basically, have the same kind of like latch interface here. So then it takes in a value, and then we'll say the value and the next value will end up equaling the value. When we get the value, we're going to return this.value. When we get the next value, we're going to return this.next value. And this is complaining here because the setter takes a number and sets a number. So we need to change that to a big int. And then we need to say this.next value equals v. And then when we latch next, this.value equals this.next value. Okay, that's actually good. That's pretty much it. For convenience, let's add in a get value low. And what this is going to do is going to return this._value and only the bottom 32 bits of that. 2, 3, 4. I put one too many in there. So when you can actually do bitwise operations and all kinds of operations on big ints, but you have to always do it on, like, both operands have to be a big int. So we're going to get the bottom 32 bits there, and then we're just going to cast it to a number. So that's useful for the rest of the program. Of course, we can do the same kind of thing for the high 32 bits. So we get value high. In that case, we don't want to add those off. We can just shift these down by 32 bits. And we'll do it for the next value as well. I don't think we're going to need the next value, but let's just do it so that we have it. Yeah, and then I think we're done with register 64. So then we can actually add these things. So let's add cycles, and that's going to be a new register 64. I don't know what TypeScript is. It's like it doesn't catch up to this. The fact that we exported this somehow. Could do the restart the server, but I don't know if that's actually going to. No. Oh. So if you do a manual import here, register 64, register 64. Okay, so we have cycles and we have instructions retired. And well, you can imagine, right, that we're going to need a latch. It would be useful to have a latch here, just because this thing is containing a bunch of registers, and each clock cycle we can just call latch next. So here we can already do cycles latch next and instret latch next. We could match like the pipeline stage interface and just have a compute method, because why not, which we'll call on every clock cycle, and then here we can just increase the cycle counter. 1n has to be a big N. So yeah, so we're just incrementing the cycle counter here. Then we're doing latch next. That's pretty much it for this. Yeah. So next, let's go into decode, and let's kind of like start pulling out some of the information about these CSR instructions. So one thing we're going to add straight off the bat is going to be, is this a system instruction? Because that is the opcode type, and the opcode for that, if we look in the spec, go to the fabled 104, this is our opcode. And actually you can see I'm highlighting the eBreak instruction here, and that is because these two, eCall and eBreak, these are also system instructions, which makes our job a little bit harder. I'm going to push that problem forward a bit, but we'll be able to solve that pretty quickly. As you will see, these are very, very easy to determine, because on eCall, every single other bit other than the opcode is a 0, so that should be not too hard to recognize. And in eBreak, every other bit is a 0 apart from this one, which is the 1. So it should be pretty easy to do. Okay, then we get our CSRs. Then we have them here, and then let's just grab this opcode, and then we can take it back. We can paste it in where it's gonna like insert a new line as well. Still haven't put any energy into figuring that out. So here we're going to get our system instructions, and let's actually maybe just look at the instruction again quickly, because where are we here? Yeah, so these 12 bits, they constitute the CSR address, and we actually pull those 12 bits out, but we do it here in the immediate, and then we immediately sign extend it. So we kind of want to grab this and have it be the CSR address. So let's make another register called CSR address, and in CSR address, what we can do is, I'm just going to put it here so that we can use that I variable, this.csr address.value. Yeah, that's just going to be these upper 12 bits of the instruction. And again, yeah, like this, like on the hardware, this actually won't be a shift operation, right? This will just be a slice. So it's not super important that we do it this way, but I'm just copy pasting it here. Okay, so now we've got the CSR address. You know, that's kind of it, right? We already got RS1. There is this idea of it also being this U immediate, and that's an unsigned immediate, right? So it just means that we're not keeping the sign around, or we're not doing like 32-bit sign extended. So yeah, we maybe want to decode that. Yeah, because we could do quite a bit of decoding here, because we can already look at funct3, which is part of the instruction that we already have. We can already determine, like, if we have an integer instruction, or if we have a register-based instruction, and we can already sort of put this, either the register value or the immediate, which has been 0 extended, we can kind of already put that into a CSR source. Just use the name here, like CSR source. So let's do that. Oh yeah, and probably worth mentioning, going back to 104, the way in which we can determine if this is an integer instruction or if this is a register instruction. If you look here at funct3, you'll notice that the first 3 have a 0 in the bit index 2 position, and the bottom 3 have a 1 in that position. So that 1 is signifying the immediate instruction, and then those bottom 2 bits just encode the kind of the type, right? The read write, the read set, and the read clear. And those are the same between the two sets of instructions. So we can just look at that bit index 2 to determine whether it's an immediate or not. And we can look at those bottom 2 bits to determine what kind of operation it is. I think we're only going to need to determine if it's a read write, actually, to get kind of all the information we need out of it. So let's do this. We can have our, let's call it the U immediate. No, let's not call it U immediate because we have that. I think elsewhere in this document they call it Z immediate, like a 0 extended immediate. So I'm going to do that. And a 0 extended immediate is actually just, yeah, we sort of don't even need to do it, right? It's just RS1 address. We don't need to 0 extend, right? Because 0 extension is a concept that really only applies if you actually have a fixed number of bits and you need a strategy for going from a smaller number of bits to a larger number of bits. So in computers, the natural operation, actually, when you do a cast, the natural operation is to do a 0 extend. Sign extension, was it sign extension if you have signed numbers, right? Because if you have a -8 in which is an 8-bit signed 8-bit number, and you want to put it into a 32-bit signed number, you probably want to preserve that value of -8. So then you're going to sign extend it. But yeah, so JavaScript, TypeScript's already doing this for us. We don't actually need to do anything special here. So we kind of don't even need to put it into a named thing, but I'll do it for the point. So is integer CSR. The way we determine that is we look at funct3, next value, and we look at the top bit, right? So we just do b11, and if that happens to be equal to this, right, that is the case where it would be, because we're just masking, and here we're comparing. So if that bit was a 1, it's the only bit that could stay a 1, then it is the integer CSR, and obviously the opposite side of that is that it's a register-based operation. And then let's do CSR Instruction Type, and we can get that by looking at the bottom 2 bits, right? So we're going to do this and OB11. Brackets for why not. So now let's make a register for CSR source. Okay, so .csr source value. CSR source is going to be, well, if it's an integer instruction, then it's going to be the Z immediate, and otherwise it's going to be this.rs1.next value. And in this whole thing, we're actually treating it like we we don't necessarily have access to immediately to the register, although we should have access to the register on this clock cycle. This is really, you can think of this just really piping that same value through to a nearly knocked that over. Piping this value to to another register, right? It's coming from the same source. So in the FPGA hardware, this is like sort of, you're just putting this value into a new register. It's the same source. I hope that was clear in some way. I don't think it was. Okay, so the next piece of information that we can decode here is this this idea of like we're looking if we're using X0, sort of our 0-based register, and determining if that means we should do a read of the CSR, like should we actually do this side effect based read, and looking also then at the source register and determining if we should do this side effect based write. And I think we're going to need we're going to need those in later stages, so let's make those first class as well, or actual registers. So this is going to be CSR should write and CSR should read. So this .csr should write. So when should we write? If we go back to the spec here and we go to here, so we always write with this instruction, right? We always write if it's the read write. This one actually says that we might not do the read if RD is 0, but we always end up writing whatever is in RS1, even if it is the 0 register. So the first part of that condition then is just going to be Csr Instruction Type. Let's actually say this is CSR RW, and then we'll compare that to OB. Wait, what is that? I think it's 0, 1. Yeah, so those bottom bits are 0, 1. So we'll just make this instruction type just be a check for is this the read write. And so the first part of this, we'll use this bool to, and this should be a.value, and we'll use this bool to int. And the first part is going to be, is this CSR read write? So we're always going to write in that condition, but or like in the other condition, if it's not a CSR read write, then we need to look at the source register address. So if RS1 address is 0, if it's not 0, then we would write. So if it's the read write instruction, no matter what, we're going to write to that CSR. And if it's either of the other two instructions, so the read set or the read clear, and the register is not 0, then we're going to do a write. So this condition should cover, that should cover the logic we need to say whether we write to the CSR or not. And it doesn't matter if it's an integer-based instruction or not, right? That's out of the window at this point. Okay, so for CSR should read, well, how does this one work then? So this one kind of only applies to, so in this case, these two always read the CSR. We always read if it's a CSRRS or CSRRC. So basically we want to know, like, is it this instruction? Like, if it's either of these, then we always do it. And if it's this one, and the register is not RD, that's when we would do it. So let's kind of put that into some logic. So what we could say here is that if it's not CSRW, or if it is CSRW and the RD address we actually have in one of these, if that address is not 0, So this is when we would read. If it's one of the two read instructions, or if it's the read write and the next value is not equal to 0. So I think that about covers it. Yeah, I think so. So that's pretty good. I think we've got everything here, right? We've got the address, we've got the source, we've got the should write, should read, and we have the is it a system instruction. So now we can just take those, wrong key there. So we can take those, and now this is where I think it becomes slightly less error prone. Is that now I can just easily do this, and that I know that all of those will be present in the next stage. We don't have to latch them, didn't have to mess around with anything, so if all goes well, like all of those values should be passed through properly. So then we can go into the execute stage, and in the execute stage we're just going to pass these things through. We don't need to do any computation in the execute stage. We're actually going to do the reads and the writes in the memory access stage. I think that's where I'm going to put it for now. I think that is an okay place to do it. At least I don't see any problems with it. If you're a RISC-V expert and you think that is the wrong place for it, just let me know, and I'll think about moving it. But I think I'll probably do it in memory access. So in execute, all we really want to do is make a copy of all of those registers and pass them through from decode. So maybe I will just do a bit of copy paste work here. Copy that, put it here momentarily, copy all of those, get rid of that, and then here we can just paste those in, and then we just want to pass them forward. So this dot the system value is going to be equal to decoded dot is system, and then we have CSR address, we have CSR should read, we have CSR should write, we have CSR source. Yep, cool. And let's put those at the bottom, and let's put is system here with the other is instructions registers. Okay, then at the end we can actually just copy paste here as well from the bottom, and paste those in. So that also feels more painless to pass values through. You can be the judge of if it feels less painless to watch. And then here in memory access, this is kind of where we want to do the stuff. And I realize, right, that we still haven't actually filled in these read and write methods, and we will do that. But let's kind of do the functional stuff here. In all cases, I mean, for now, keep forgetting the fact that we have those two other kinds of system instructions. For now, if we have an is system instruction, and I'm just going to pull that out from here, then we can say that we're going to read something out of the CSR and put it into the register, right? And that's not always the case. Well, for us, actually, it doesn't matter, because the case where you wouldn't write something, right? If we have this like this idea that, well, it's dictated if your destination register is X0, right? That's kind of when you say you don't do a CSR read, right? But we can kind of say that we're going to write to the register even if it's X0, because for us, writing to X0 is going to have no effect anyway, and we're just going to pass it like a junk value that has no real meaning. So it's fine to just add is system to this write back value operation. Okay, so let's add if is system here. By the way, know that I'm going to create a bug here because we haven't dealt with the idea here. Like if we have a system instruction, we're going to end up running into this not implemented thing. So I'm just going to add the this.isSystem.nextValue. No op. You know, it's nothing happens there. I just want to make sure that we don't end up going into this error. But if we have a system instruction here, well, now this starts to become interesting, right? Because now we have to look at what kind of instruction we have, right? Which of those 6 is it? And we can start taking out our CSR address, whether the CSR should read, whether it should write, address, and the source. Yeah. So now, how can we do this? We kind of always need to read the CSR, right? So let's say CSR, let's do it like this. CSR value is, and then we can say if CSR should read. Well, in that case, we need access to the CSR object, and there is no CSR object, right? That's not something we have right now. So let's put something here. Say that we need access to a CSR interface as one of our inputs. We haven't provided that in the stage, but let's just say we have it now, right? So now we have a CSR. We can do a read, and we can pass in our address. So that's already just CSR address. If we shouldn't do a read, we'll just put this as 0, right? It doesn't matter. So then we're going to have to do something conditionally based on what instruction we have. And for that, I think we should make an enum. And I think we should put the enum inside the CSR directory. I can just put it here. I don't know why I made a directory, actually. It don't necessarily need one, but let's make an enum, and it's going to be Csr Instruction Type. Go back to the spec, back to 104, and so, yeah, I think I remember these actually. So let's see if I do. CSR RW, that is going to be 0, 0, 0, 1. And then we have RS, it's actually 1, 0, and then RC, 1, 1. And then we just have those 3 again as the integer variant, which just has a 1 in those bits. Okay, so now we can switch on the instruction type, and the instruction type is just in funct3, right? So we have funct3 available to us. And so case Csr Instruction Type dot well, the only one we actually really need to do here right now is this RS. I think I might do them all, but the only one we really need is RS, which is read and set. And so we've already read the value, and that's going to become our write back value now, right? Wait, maybe we don't even need to put it into a whole separate thing. Maybe that just becomes our write back value. That might be the case. No, we don't assign to next value, we assign to value. Yeah, so I think that just is our value now, right? So what we're doing now is, if if we should write, CSR should write, then we can say this.csr.write, and we're going to write to the CSR address, right? So we're just reading it and we're modifying it, writing it back. And the modification we're going to do is quite simple in this case, right? Because we're just setting those bits, and they're literally the bits that we have in our source, our CSR source, either the immediate or the what we had in RS1. And yeah, so the way we set is we just take the current value, so that's going to be the write back value, this.write back value dot next value. It would be better to give it a name, and I think I'm just going to give it a name quickly. Let's go back to CSR value, and then we'll just assign that at the end of the thing. It's this value ORed with the source, the CSR source, and that's all we need to do, right? Because if you OR something, you're just going to add, you're going to like put that one bit, always going to, if there's a bit that's a 1, it's going to go in the new number. Because, you know, 0 or 1 is 1. 1 or 1 is 1. So we'll end up setting those bits in that way. Yeah. Cool. So that's what we have to do. I think what I'll do here is just say this.writeBackValue.value is CSR value. I already do it here, right? It's just for having a nice, useful name. So that's how we do that, and that's all we need to do, right? Then we can break. I think that's actually, I think that's true. So what about if we have a read-write? So then Csr Instruction Type dot read-write. Let's put this up first because it is the first one. In this case, if we should write, we're going to write, we're just going to write the whole source, so we're not going to do an OR operation. So I think it's going to be pretty much the same kind of, copy paste this here, we're just going to write the source now. And by the way, it's going to be up to the CSR interface to decide if something is rewrite, or if like if when we do a write, like only some bits end up getting written. There is this whole concept in the privilege spec that talks about like the kind of like writability, like the permissions of each register, and there is this idea of write. I'm gonna get it wrong now. Yeah, like WARL. So I think it's like write anything and then read logical. And then the idea is that you can write anything you want to it, but it might ignore some of the bits, or it might ignore all of them. But like you're allowed to write it. It's not that you can't write the register. There are such things as read-only registers, but something might be writable, but just do nothing with your write. So in this case, we're just going to do a pure write, and we are going to break afterwards. So quite simple. And then we're just left with the clear version, which is, you know, this will be the most complicated, not that complicated. Now we need to clear the bits in a particular register, right? And the way we do that is, well, let's imagine our value is, let's just do 4-bit numbers here. So 1, 0, 1, 1, 1, right? And then our source is, let's say it's 1, 1, 0, 0. So we want to clear the bits in the top 2 positions, and we leave the other ones alone. Well, how could we make this happen, right? We can't do this OR operation, obviously, because that's just gonna put a 1 here. So what we want to do is we want to explicitly get rid of the other bits. So what you can kind of think about there is, yeah, I'm tricking myself up now. How do we clear bits? You have to invert the, so we would take these bits, right? And then we have these. And then you can imagine, right, that we're trying to clear those two. So what we want to do is we want to invert this whole thing. So that would give us 0, 0, 1, 1. And then we would, then we can OR them together, right? So we invert it, and then we OR it together. Am I thinking right about this? No, we can't OR it. No, we're going to AND it, right? We're going to invert the bits and we're going to AND, right? Because if there was a 0 here, for instance, we would want to keep that as 0. So an AND operation is going to make sure that we only set the bit if it actually is set. So the idea is that we invert the source. So we'll do like something like this. New value is, you say value, and then we'll invert our source. Where is my tilde key here? Yeah. Invert the source and those things together. Yeah, and of course, like we need to account for the fact that we need to limit this to 32 bits. So yeah, that's going to be the CSR value ANDed with the CSR source. And we're going to actually, we don't actually need to do anything with those other bits. The only thing we would potentially need to do here is twos this again. So let's do that. Let's put in the twos. That should be it. Kind of waddled my way through the clear operation, which I always have to think about. And now we have, for all intents and purposes, actually implemented the thing, because we actually don't care. Like, we shouldn't actually look at funct3, right? We should only look at the bottom 2 bits of funct3. Oh, this is kind of stupid. I think I'm going to do this, which feels ugly somehow, but I think I don't even know if we're going to need these things. I'm just going to have the idea of like the generalized operations. So we'll have those: read write, read set, read clear. And then here, I'm just checking those, right? Because we only want to look at those bottom 2 bits. Because we've already covered the idea of it being the integer instruction by the fact that we multiplexed into a source. And with that, I believe that's actually done. So now we're just onto the final stretch, and the final stretch here is like the pipeline stuff is done. The only thing we haven't done is wired everything together. You'll see we now have an error here because we don't provide access to a CSR. Let's actually put the CSR space onto onto the main RV32i system, and then we can very easily pass CSR as this.csr. That's then happy. And what we need to do is actually go and implement this read and write. And to do that, we're going to finally take a look at the privileged specification. Now, let's just roll up. This is the RISC-V instruction set manual. It's volume 2 of the privileged architecture. So this document goes into a lot of stuff, right? This goes into many more of the architectural details that go into making this multi-privilege system. It talks about CSRs. It talks about the behavior of different modes. And the only things we're going to care about here really are the CSR listing and the addresses. And in the next episodes, we're going to be looking into this machine level ISA and the machine mode privilege instructions and some of the things that come with that. And yeah, we're probably actually going to do that over the course of a few episodes because it's going to be a whole set of things there. It's not quite as much as it maybe looks like now, but yeah, there's a bit to do there. Okay, so I'm not going to waste any time. I'm just going to jump into this chapter 2 about control and status registers. There's a whole bunch of information about how they're encoded. And the kind of nice thing, and we can see this here, is that not all 12 bits are used to kind of just arbitrarily address random CSRs. Like different bits actually encode meaning as well. So these top 2 bits, they actually encode the privileges. So for instance, if it's 1-1, those top 2 bits, then it's a read-only register, right? And if it's not 1-1, then it's a read-write register. So that's already something that's just very useful there, but it takes away 2 bits of address space. So 12 bits is 4K, right? 4096 different values. And we get 1/4 of that taken away. Like we end up with 1/4 of that after using these 2 bits to encode this. Then the next 2 bits are actually just used to encode the privilege level. So you'll notice here that we've got the user level CSRs, we have the supervisor CSRs, hypervisor CSRs, and machine mode CSRs. And we can just completely ignore everything in the middle here because we're not going to have a supervisor or a hypervisor. And so yeah, so then we're left with these bottom 8 bits. And in the bottom 8 bits, it basically gives us it gives us a space here to do certain things. And so we have standard read-write CSRs, and then we have custom read-write CSRs. And if we were doing something with the LEDs, for instance, or some other configuration of the board, maybe the UART configuration or something, we would use one of these custom slots. That is allowed for implementation purposes. And then the standard stuff, that's going to live in these other places. And then, of course, for the read-only part, there's some standard stuff, and then there's custom. And then by the time you get down here with the machine mode stuff, which we'll look at in the next one, you have a couple more possibilities. But yeah, like they don't really add anything. There's just a bunch of space for read-write, a bunch of stuff for read-write and debug only, custom read-write. Yeah, you kind of get the picture at this point. So, we are actually going to ignore all of that stuff that's here. These are like now specific CSRs. So we've got the addresses here on the side. And we've got the privilege level, which is also encoded into the address, right? So it's a user mode read-only address. And so here we have the cycle counter. And so the address of that is C00. The address of the time is C01. The address of instruction return is C03. Then we have a bunch of these HPM counter N. And that's actually some sort of performance counter, and it's not necessary to implement this. I believe RISC-V mandates that we make it possible to read something here, so you don't just give nothing back, like you don't make an exception happen at this point. We'll talk about exceptions in the coming episodes as well. But we're not going to implement counters, like anything special going on there. Then you can see we have the upper parts here, right? The high 32 bits of these. You can see it's RVI 32 only because, yeah, if we had a 64-bit or 128-bit processor, we wouldn't need these parts. But they live at C80 and C81 and so on. And so that's kind of all we need to know, like these addresses and how to do the decoding. So let's actually go back. Let's start in the read. And let's kind of pull apart some of these things, right? So let's take a look, right? To get what's the first thing, right? Up here, this is going to be whether it's read only or not, right? So is read only. And it kind of doesn't matter, right? Because we're doing a read, so there is read-only decoding is completely useless to us. But for that, we take the address, this 12-bit address, and we just want the top 2 bits, so we can just shift down by 10 and just get rid of those bottom 10 bits, just be left with the top 2 bits. So next is the permission, and for that, well, like you can see that the permissions, they're like 2 bits down, right? They're in bits 8, 9. So we can actually just shift down by 8 positions and then mask off the appropriate stuff. So we'll do address 8 and then just get the 2 bits that we care about. So that gives our permission. And then we can take what maybe I'll call the true address. And that's basically just the bottom 8 bits. So we can just mask those off in the normal way. Great. So right now, if the permission is not the user mode permission, right? Because that's the only thing we're implementing now. So if it's not 0, then we're going to throw an error. So let's throw new error, only user mode implemented. Just put CSR read here as well, just in case that happens. We would know anyway. And if we make it through that, we don't care about is read only, sort of like useless there. But if we make it through that, then we just look at the true address. We could actually just look at the address, right? We don't really need to look at the true address, but no, let's just look at the address in general, because we're going to need to do some machine mode stuff. Let's forget true address for a second. So if we have C00, and that is, scrolling down here, that is our cycle counter. Or in that case, we're in the cycle counter, it's the bottom 32 bits here, right? These are the high 32 bits. So if it's this, then we would simply return this.cycles.get value low. Not get next value low, we want to get value low here at this point. Just going to do this to make sure that I don't make a mistake here. Now the next one is time, and like I said, right, we're just going to use the cycle counter for time. So we'll make that one C1, and in the C2 position, that's our instruction retired, so instructions retired. Now we can also just do the upper part here. Luckily, they just set one single bit here. 80 hex is just 1 and then 7 zeros. So there's just one extra bit here. So we can just check the same 3, but with an 8 in the hex number there. And then instead of get value low, we're going to do get value high. And that's it. For everything else now, we're actually going to return 0, which is not strictly accurate right now, but that'll work for now. And for write, well, let's grab the same stuff and let's kind of paste it in. So if it's read only, that's actually going to be a problem, right? So we can have the same problem with the permission, and now we can have a new error that can happen if it's read only, right? If it's read only, if it's read only, we actually need to make an exception happen, and this is kind of our stand-in for that right now. And yeah, actually all of this is going to go away because there is no, none of those registers are writable, right? The registers that we're implementing right now, they're not writable. So nothing happens here. We don't do anything with value. That is our implementation. And well, I'm sure I've done something wrong, but if all has gone well, we've kind of implemented CSRs at this point, at least the user level stuff. So how can we test this? Well, the way I would like to test this is by writing some C, but we don't have any way of of actually calling these like these special instructions, right? If I go back to the regular spec, or the one we've been going from, volume 1, the ISA, the user mode ISA, and we come down here to the assembly programmer's handbook, there is a pseudo instruction for each of these. And that just corresponds to this kind of assembly, but like we don't have a way of doing this in C, right? This is literally just an assembly instruction, but we can actually do it. We can use the ASM keyword, which allows you to do inline assembly in C. It's actually pretty cool. So let's make here a variable called result. It's uninitialized at the moment, so it doesn't have a value. And what we're going to do is we're going to use this ASM keyword, and it kind of looks like a function, but it's not really a function. And in here we can just write some assembly. So let's read the number of cycles first, right? Because that's easy. Maybe let's read the number of instructions, because I realize now we haven't implemented the instruction part. We can do that really easily if we go into the main RV32i class, and we come down here, right? We have this cycle where we compute and latch, we have our debug stuff, and here we check like if we're coming from this state, we've executed this state at this point. And if we were like in the write back state, then we've done the full instruction cycle, and we're going to go to like fetch the next instruction. So let's just put it in here, because why not? Like we can do this logic here because we have this super linear pipeline. So we can actually just say this dot CSR, and I don't really like this, but I'm going to do it for now. I feel like we should have some interface for actually like saying like just calling or something like that. We shouldn't be doing an addition here. This doesn't make any sense. But I'm going to do it here just for like trying to keep this somehow sort of some semblance of short. Alright, so what we want to do is an rd instret, instruction retired. And yeah, so what we're doing here, right, is we're just trying to read the number of instructions retired, and we want to put it into the into a register, right? That's what this does. And so we give a destination register. The nice thing about doing inline assembly in C is that you can sort of use this sort of like templating kind of syntax, and instead of specifying a register, you can just put %0, or actually you can use more things, and then you use this weird colon syntax. So this is really not a function. This is really like specific syntax. So you know, if you want to learn about it, go and Google it. It's yeah, there are some things you can find out about it. And what we can do is actually get it to put that value inside this variable instead. And the way that we do that is that we say equals r. So it's basically like take the first register, right? So I guess we could do these in order. Take the first register and just basically generate the code that would take that result, like what would be in that like sort of destination register, and put it into the result variable itself. That's kind of a good enough program for what we're going to do. So I'm actually going to, I'm in the system code, so we can just run make. So I've built a binary now. We can very quickly just look at the dump for that. So let's just do RISC-V object dump d main.o. This is the assembly we generated. Super simple. We've got our general little prelude bootloader, which basically sets up the stack and jumps to the main code. Then the main code does a little bit of stack pointer and frame pointer stuff itself. And then finally, here at this number instruction, we end up running our rd instret and putting the result in A5. And then you can see we end up storing A5 into the whatever the current stack is, offset by 20. Basically here where we did this add immediate S0 SP32. Oh no, that's not true. We just reserved enough space. We didn't need to initialize it, and then we put our value there. So that's why it has 32 here. It's taken 32 bits of space, and then we've stored our 32 bytes rather, and then we've stored ours at offset 20. So that's enough. Let's go and try and run this. Probably I've made mistakes, and so we might need to do some debugging. All right. So TS debug. I've no idea. Yeah, probably didn't work because this breakpoint is. I don't even think we have that. We don't even have that address. We need to put a breakpoint. Yeah, let's put a breakpoint here at. Well, let's put one at 1C. Let's be really optimistic and see if we actually just manage to execute it correctly just by analyzing the output of the program. That would be great. So I'm going to put a breakpoint here. Let's see if we even pause the program. We don't. So something crashed. I made a mistake somewhere. Let's see what the error message is. Not implemented. That's in decode 112. Okay, so let's take a look. Decode 112. Okay. I expected that we would succeed there. So let's see what is going on. If is system next value, no op, otherwise not implemented. Okay, we were too optimistic. I'm going to put the breakpoint on the instruction itself. Hopefully this stops. I think I messed that up there. Okay, so we're getting not implemented even before that. Okay, let's put a breakpoint here and see where we are. Oh no, started in the wrong place. Start here. Okay, we actually get to this point. So we have the PC here. So this dot PC dot next value. I guess we also just have a PC toString 16. Where are we? We're at the very first instruction. Okay, so the very first instruction is load upper immediate. So what's going on there, right? We have is load upper immediate. So I would have expected that that was a 1. Huh. How did we even end up here? I'm really confused as to how we even get to that point. So jump there. Load upper immediate. Next value is 1. So we should come inside. Oh, yeah, that's pretty stupid. I thought it was an else if, but it's just an if. Okay, so that's pretty stupid. Let's go optimistically back to 1C. Oh, I love these moments of debugging at the end. All right, we actually hit the breakpoint, so let's have a look. So you will remember that we're here, and A5 is at the index 15 in the register file. This dot reg file 15. Oh, the suspense. All right, we got 0, so that's not correct. Let's have a look. Let's see if we are actually. We should. Like, what's the PC here? We are definitely at the right address, right? PC toString 16. Yeah, we are at the right address. Okay, so what I think I'm going to do is, there's a bunch of things that could be wrong here. Let's put a breakpoint. There's just too many things that it could be. So let's put a breakpoint here at 1.8. So now we shouldn't have executed the instruction. So I want to just jam one here at in the decode, and let's actually make sure we're in the right place. So next value, yeah, okay, so we decoded. So we have a CSR source, and our CSR source next value is 0. That makes sense, right? The source, if we look at the spec, right, and we're doing RD time, RD instruction, right, it doesn't actually matter. We're going to do a CSR RS. We've got RRD and the address of this thing, and X0. So that's our source register, right? X0. So it actually is 0. If we were to look at is integer, it would be false. Our Z immediate would be 0. It doesn't matter. And is read write. Yeah, so it's not the read write, right? It's any of the other ones. So okay, that all looks good. So I'm going to assume this is all fine. Let's go to the memory access stage where all the action really happens here. And jump here. So is system is a 1. Okay, so that's good. So we should be writing something back to a register. Let's come down into here. CSR should read. It should read. So that's actually also good. And what's the address actually? 3074. 3074. ToString 16 C02, and I believe that is the correct address. This is the wrong document. Let's go to the other document. 02 instructions retired. Okay, so that's looking good. So let's actually follow this in. Let's like jump down. So we're going to get the is read only, is blah blah blah. And here we make it through the permission check. We get here, we actually get to this point. So let's jump into this part. And here the value that we have is 0. So have I made a mistake just in this class? Like when we latch this dot value? Oh, wait. Yeah, that's okay. So the thing is, next value is actually 1 here. Oh, no, I know what's going on here. We didn't wire up the latch or the compute or anything, so this is not going to work yet. CSR.compute. That's going to count cycles for us. And then the latch next, yeah, we need to do that too. Okay, that's hopefully a straightforward one. Let's try this again. Yeah, we're going to break in places we don't want to break at the moment. Okay, so we got the debugger. We were on the instruction before, so we could actually drop the breakpoint in, follow it through. Why not? We're here. Okay, so I'm just going to go through CSR value 6. That's promising. So the write back value becomes 6. We go in here. We're going to see which kind of instruction we have. We should have RS. We do. The CSR should write back at 0, so we don't do any write back. We skip it. And that means we're going to write, we should really write that value to the A5 register. So now we're before we are, if we go back here, we're now on this instruction. We haven't actually executed it yet, but it doesn't matter because A5 should contain, at this point, should contain the value. And it's got the value 6. And let's actually just double check that that is correct, right? 1 instruction, 2, 3, 4, 5, 6. And it was 6 before we executed this instruction, right? It couldn't be 7 because it hadn't finished writing this instruction. So that is correct. That's perfect. I'm really happy with that. Yeah, it's brilliant. let's try with another. Let's try with the cycle counter. So let's just modify the C file, and instead of doing rd instruct, let's do rd cycle. Is it cycle or cycles? I think it's cycle. I'm looking in the wrong place. Yeah, cycle. Okay, so we can compile that, and then we can run it. I expect actually that like the structure of this program would stay the same, only that one instruction should change. So yeah, it's still at the same one, and it runs A5. So that's yeah, let's take a look. Sorry, I realize I just ran that command without showing you, but I just dumped the program again, and you see that only this one instruction changed. So all the other addresses and everything, they're all the same, because why wouldn't they be? Okay, so let's actually change the breakpoint to be the one after, because we can hope that it just works. Run debug. We got to the debugger, and at this point it's also going into A5, so let's take a look. We get 33. Now let's try and work out if that makes sense. So we know that we have 5 instruction stages. Right now, every stage takes 1 clock cycle, which is not actually accurate. We're going to change that soon at some point. Every clock cycle, it takes 5. So every instruction takes 5 clock cycles, basically. So this is 5, 10, 15, 20, 25, 30. And then, of course, this is not actually executing until the... we're not actually reading that value until the write back stage. So we have 30, and then we have 31 for instruction fetch, 32 for decode, 33 for the execute stage, and then it would be 34, but that's actually the stage that we're in when we run this, and so we read 33. So that is also correct. All right, that's actually brilliant, and I'm really happy with that. That's a yeah. I'm sort of we got some problems with that, but I'm glad it actually worked out in the end. So yeah, if we now go and take a look at the big list, which we try and do after each episode, we've now knocked out this little batch of instructions, right? Obviously, we haven't like implemented all the CSRs that we actually need to implement, but the instructions themselves have been implemented now. So we have those, we have all the arithmetic, we have basically everything up until the top, only not add up or immediate to program counter. And like I say, I might actually do that in between, I'm not sure. And then that will actually only leave us with these 4 instructions. And just like I mentioned every time, fence will be a no-op. And eBreak and eCall, I think we will do something with eCall. eBreak will probably also be a no-op for now. eCall is going to have some minor significance for us, probably. I think that's how we're going to do interrupts. And so, yeah, at some moment we might have some software-driven interrupts, although we might only have hardware-based interrupts. I'm not sure yet. So that's it. It's been a bit of a long one, but we've covered a lot of ground. Thank you for watching. If you're a patron of this channel, thank you very much for supporting the videos. I truly appreciate it. If you want to become a patron, you will generally get these videos about 1 week before they're released on the main channel. And I also put updates out there periodically, although not as often as I should. If you want to discuss this, leave me a comment in YouTube or in Discord or in the low-level JavaScript subreddit, but that's a bit unloved lately. Yeah, Discord's the best if you want to have a real-time discussion, but of course you can just leave a comment. Yeah, have a really great rest of the day, or evening, whatever time it is where you are, and I'll see you next time.